Hello everyone, how are you doing? All are doing good? That's good. I'm Mahesh, your physics teacher, and you're watching me on SMR Online Physics. Yeah, this is a continuation series on the topic of refraction of light. If you're new to this channel, do watch the video. If you like it, press the like button. Do share it among your friends and subscribe to my channel SMR Online Physics for all the latest videos coming up on the various topics of physics. So let's get started in this class. I'm going to talk about a very interesting but important topic called critical angle. Okay, here we go. We'll talk about critical angle, and this is also related to our topic of discussion, that is refraction of light. Alright? So when does this critical angle come into play when we actually discuss about refraction of light? Let me just get to you right. So we know what is refraction of light and why does light exactly refract. So if you look into this diagrammatic representation, this is my interface, and critical angle comes into action when we deal with a ray of light actually traveling or propagating from optically denser medium to optically rarer medium. Okay? First of all, I'd like to show you the original case, what we exactly know like. If a ray of light travels obliquely from denser medium to the rarer medium, and this is our normal, and if the angle of incidence I is lesser than, let us call theta c, where theta c I use for representing the very important critical angle of incidence. So if the angle of incidence will be lesser than the critical angle for this given pair of medium, then this ray of light, instead of going in its original straight path, actually would speed up and start bending away from the normal, which we very well know. And some bit of light will definitely get reflected back. That we discussed in our previous classes, which is very, very normal, and this is our angle of refraction. Clear? Okay. Now we'll come to a situation number 2. The situation number 2 is, still I deal with the same pair of medium. Now the curiosity increases. Why I mean to say that, this is my normal and my curiosity increases in the case what will happen if I increase the angle of incidence when the ray of light passes from denser to rarer medium. So suppose now the ray of light is incident again from the denser to the rarer medium, but this time I have purposefully increased the angle of incidence, and this angle of incidence I has exactly become equal to the critical angle of incidence. This is, my dear, what I call as critical angle of incidence. Now for this angle of incidence, this ray of light, this is our reference line. We prefer that it should have gone, might have gone straighter, but never it happens so. For this critical angle of incidence, if it is truly the critical angle, then the refracted ray doesn't appear in the rarer medium. Rather, the refracted ray goes along the interface of the two separating media, creating an angle of refraction which is equal to 90 degrees. This is what we call as critical angle of incidence for a given pair of medium. One important noted point here is, it is always obeyed or observed when the ray of light travels from denser to the rarer medium. Alright. So for this critical angle, if I is exactly equal to the critical angle of incidence, then we find that angle of refraction becomes exactly equal to 90 degrees. That's it. Now you will be still getting more curious about it, okay? Just excuse me. If I increase the angle of incidence beyond the critical angle of incidence, what would happen to the refracted ray of light? Will we ever find anything getting refracted into the rarer medium? Okay, so let me show you. I would like to rub off this first case because of a bit lack of space. All right, okay, good. So again, I try to show you the third case. This is my interface. This is your rarer medium. This is your optically denser medium. This is your preferred normal. And now you see what's going to happen. If the angle of incidence, my dear, is much more larger, if this is your angle of incidence for this particular case, where angle of incidence is observed to be greater than the critical angle of incidence, then the very interesting part exactly takes place. The interesting part is that now I don't find any refracted ray in the rarer medium. Please get to your head, both are still the same transparent media in which we always expect the light to actually propagate through. But if your angle of incidence is greater than the critical angle of incidence, then you will find the entire ray of light reflects back into the same denser medium. So this will be your angle of reflection rather than angle of refraction. This specialized phenomena has a lot of importance, which I'll be discussing in my next video class. But for time being right now, this is what we call as total internal reflection of light. Please mind the spelling and the pronunciation. I said it is total internal reflection, even though we are dealing with two transparent media. I hope you are enjoying it, okay? This is very good, important information. This is only possible when angle of incidence is greater than the critical angle of incidence. All right? I'd like to show you the relationship between the critical angle of incidence and the refractive index of the denser medium. All right? So I'd like to redraw the diagram. This was our rarer medium. This is our denser medium. Please observe it closely. Students tend to get slightly confused up in such cases. This is our preferred normal, but everything should be clear on SMR online physics. So here, suppose a ray of light is incident on from the denser to the rarer medium, and this is your exact critical angle of incidence for this pair of media. So definitely you'll find the refracted ray passing along the interface, creating the angle of refraction to be exactly 90 degrees. So my dear, as I already discussed in the previous video classes, so I will be treating this denser medium as medium 1, and here I have the refracted ray, so the rarer medium as medium 2. So how should I write a relation to find out it? So we have N21, which is easy to remember for most of us. N21, I'm finding the refractive index of the rarer medium with respect to the denser medium. So the formula should have been sine of I by sine of R. Hope I'm clear, right? So if I continue to do this way, then NRD, I'm finding the refractive index of the rarer medium with respect to the denser medium. So the rarer medium in most of the cases is our air or vacuum medium, and this could have been glass, this could have been water, the denser medium. So we'd like to express the opposite. So I mean to say this would have been written as 1 by NdR. So 1 by NdR, which is the reciprocal of that refractive index, is equals to sine of theta c by sine of 90 And I'll expect that most of the students attending my classes definitely know sine 90 is equals to 1. So you will find that NdR, my dear, NdR will be equal to 1 by sine of theta c. Very simple to see that. Or you could have written the absolute refractive index of the concerned denser medium in your question is equal to 1 by sine of theta c, or you could have directly written sine of theta c is equals to 1 by nd. Or to find out the critical angle of incidence, we could have written sine inverse of 1 by nd. I think it's clear to all of you. So the critical angle of incidence is equals to sine inverse of 1 by absolute refractive index of the denser medium. Hope I'm clear. Good. Okay, just note it down. Example of what exactly this number or the angle of incidence, which we call critical angle, mean to for a given pair of media. Okay. So let me show you quickly. I hope all are getting it right. Okay. So for example, the refractive index of glass with respect to air, which is absolute refractive index, is well known to us. It is around 3 by 2, okay, 1.5 that is. So for this pair of medium, means for glass and air medium, what would be the critical angle of incidence? So all what we have to do according to the formula is sine inverse of 1 by 3 by 2. So hence we will find theta is equals to sine inverse of 2 by 3. So look for your sine inverse tables or just try it in your scientific calculators, and you will find that the critical angle of incidence comes out to be around 42 degrees. I am showing just an example. So what does this 42 degree exactly mean for glass air medium? It means that if the second medium, the rarer medium is air, and the denser medium in the question is glass, whose example we have chosen over here. So it means that if you allow a ray of light to be incident from glass to air medium in such a way that the angle of incidence is exactly equal to 42 degrees, then you will find that the refracted ray of light would lie along the interface, creating an angle of refraction to be equal to 90 degrees. Clear? So once you have understood what is critical angle of incidence, the next class will be supremely interesting in understanding what is total internal reflection. Alright? Please talk about the factors which can affect the critical angle of incidence. Factors affecting the critical angle of incidence. Alright? What are the factors affecting the critical angle of incidence? That can be easily always seen if you remember that formula, that sine of theta c comes out to be 1 by nd. So my dear, you can clearly see from here that the critical angle of incidence, theta c, is inversely proportional to 1 by nd. Inversely proportional to the absolute refractive index. Alright? So if this is inversely proportional to the refractive index of the denser medium, we also know that the refractive index of a medium is inversely proportional to the color of light, that is inversely proportional to the wavelength of light. And also refractive index of a medium is also inversely proportional to the temperature of the medium. We remember that, where T stands for temperature of the medium concerned. Higher the temperature, lesser the refractive index. So from this, I can easily conclude that number one, the critical angle of incidence, since it is inversely proportional to lambda, the critical angle of incidence will be directly proportional to lambda. So what does that mean? It means that, as we know, for violet light, whose wavelength is the smallest, critical angle will be the least, and for red light, for whose the wavelength is the longest, the critical angle will be the largest. That is the meaning of that terminology, right? And the second conclusion, what I was talking about, the dependence of refractive index on temperature of the medium, okay? So we can easily see that it is again inversely proportional to the temperature. So we can say critical angle of incidence will be directly proportional to the temperatures. It means that larger the temperature of the medium, lesser is the refractive index. Lesser is the refractive index of the medium, larger will be the critical angle of incidence. Hope I am very clear. Alright? So please review this short module on critical angle, know it well, learn it well, then come back to my next class on total internal reflection. We'll have great fun. So here I end up my today's class. Thank you for watching. If you have liked the video, do like it, share it, and subscribe my channel SMR Online Physics. Stay healthy, stay safe. See you again in my next class.